Hello everyone, my name is Ákos Sodri. I am from the University of IROS2022 and my presentation is entitled as Adaptive Gradient Descent Extended Kalman Filter for Pose Estimation of Mobile Robots with Sparse Reference Signals. Localization is about to obtain the best estimate of the robot pose, and this is done in a sensor fusion framework. We focused on magnetic angular rate and gravity sensors, which can be combined with GPS modules if outdoor localization is performed, or with radio modules if indoor localization is executed. The general problem is that these observations are both inaccurate and discontinuous due to the environmental changes, and this results in that the localization often depends solely on mark data. And this mark-only post-propagation is a critical task to be handled, since there are many error sources which influence the state estimation quality. Our goal was to drive such EKF structure which handles these error sources effectively and executes reliable mark-only post-propagation in reference-denied environments. We were also interested in a formulation of adaptive strategies which could be used to further improve the state estimation performance. Mark-based navigation estimates the position, velocity, and orientation of the moving body. We considered sparse update measurements. These are planar measurements in every TO second, and we had imperfect mark measurements at significantly higher rate in every TO second. The formulation is capitalized on the mark model, which captures the imperfect nature of these measurements. If proper calibration is executed, then the true angular velocity and linear acceleration vectors can be extracted from this model, and this fundamental 10-dimensional post-propagation is formulated. We extended this model with a bandpass filter, which acts on the external acceleration vector. We did this to suppress both the drift and high-frequency noise components, and this resulted in a 25-dimensional state space representation, which is driven by the accelerometer and gyroscope signals. This model was utilized in the prediction phase of the EKF in order to obtain the a priori estimate. We proposed 3 correction signals. On one hand, a gradient descent quaternion updates was proposed at TS rate. Then if the robot is characterized by motion constraints, then these motion constraints can be considered as pseudo observations. So for example, in case of the wheeled robots, we have the lateral velocity and the vertical velocity, which can be approximated with a 0 vector and supplied at TS rate to the observation model. And in the third place, we had the sparse planar position measurements, which are supplied by GPS or radio modules. Based on the correction signals, the observation model was formulated, and it mapped the state space into the measurement space. This observation model was utilized in the update phase of the EKF in order to obtain the a posteriori estimates. We established a test environment in which the filter performance was evaluated. And the ROS was used with the gazebo physics simulator. This enabled us to register both the ground truth pose data and the raw mark measurements. The Husky robot was used in these experiments, which performed various motion, and in this way, a comprehensive database was generated. Then we established an optimization framework. We used the particle swarm optimization to fine-tune the EKF parameters based on a multi-objective fitness function. This evaluated the planar position estimation error, the planar velocity estimation error, and the orientation estimation error. This figure highlights the performance results of 4 EKF variants. Basically, these EKFs can be distinguished whether they contain virtual observations and or bandpass filter. Based on our analysis, the best performance was achieved by the EKF, which incorporates both virtual observations and bandpass filter. Thereby, we concluded that this bandpass filter indeed significantly enhances the performance. This performance can further be improved with virtual measurements. This figure highlights the real-time performance of each filter. As we move on row by row, we can observe that the performance is getting better and better by augmenting the EKF with these additional features. We also derived an adaptive strategy. This varied the EKF noise covariances based on the instantaneous motion dynamics. We introduced two real-time measures, a linear acceleration measure and an angular velocity measure. These are basically integrated Euclidean norms of the accelerometer and gyroscope signals. Then we compared these measures with different threshold levels, and in this way we classify the instantaneous motion. And then the weighted sum of the classification results determine the EKF covariances. This figure highlights two things. On one hand, the comprehensiveness of the generated database can be observed, since the Husky robot, it is shown that the Husky robot executed both slow motions and highly accelerating and rotating motions. On the other hand, this figure also validates the introduced adaptive measures. Since we had the ground truth data, the ground truth based scenario characteristics could be compared to the adaptive measures. The left side of the slide highlights the performance enhancement which was achieved by this adaptive strategy. So we augmented the EKF with this adaptive strategy, and in this way 13% performance enhancement was achieved. The real-time performance is shown in the right side of the slide. This table summarizes the performance results in terms of the fitness function values. It can be seen that this adaptive EKF outperforms the other EKF variants. That was my presentation. Thank you for being part of it.